Hey guys, welcome to the last video for chapter 7.1, where we're going to be looking at half-life. So first off, some of the learning objectives for this lesson is to sketch a decay curve for the half-life of an element as an exponential function, calculate the half-life from a decay curve. So first off, some basic stuff about radioactive decay. Um, First thing is that we don't know which nuclide in a sample will decay. So what we're really talking about is that we have a large sample with a number of, let's say, uranium inside of it. Okay, so there's a large number of that, but we don't know exactly which of these guys is going to decay in one of the three ways that we've learned. What we do know, though, is the statistical probability that a nuclide will decay. So we can find out the probability in which one of these guys will decay. Radioactive decay is a spontaneous event, meaning that it's unaffected by external factors such as temperature or pressure. The radioactive decay varies as fast as microseconds to billions of years. So this really depends on the element that you've got. Furthermore, there is naturally occurring radioactive decay, which is known as background radiation that I've got highlighted in red there. These comes from pretty much everything around you, from rocks to cosmic rays, and this will be part of some of your calculations. But most of the time, it is isolated in most of our studies for radioactivity. Radioactivity is measured using a Geiger counter. It is measured in BQ, and this is, you can check out this scientist. I think it's pronounced Becquerel. I think there's a slightly different pronunciation, but Becquerel, I think, is one of the accepted pronunciations for that. So Henry Becquerel is sort of one of the pioneers in radioactivity. And 1 Becquerel, or BQ, is defined as 1 decay per 1 second. Okay, so let's look at some examples to wrap ourselves around something a little bit more concrete. So here we have a first example where, yes, this is an exponential curve graph or exponential decay. And this is very typical of a half-life graph. So you can see here that I've actually highlighted some of the key points here, which I'll just re-highlight over one more time with orange. And this is telling us, so what we're looking at is how long it takes for a sample to half. So 80 to 40, 40 to 20, 20 to 10, and if it was long enough, from 10 down to 5. And actually, that is actually right about there or so. So if we look at each of those, it takes roughly about 2 days for that to happen. So we write the half-life T1 half. So the half-life is 2 days. Okay, so that's a notation that we're going to be using. So let's have a look at a few more examples. Example number 2 here, the activity of a radioactive sample has an activity of 761 BQ, becquerel. Determine its activity after the lapse of 3 half-lives. So first off, let's get this number out here first. I'm going to go back to black here. So 761 and 3 half-lives. So it's actually 3 times, oh no, not 3 times 2. This is where it's going to mess you up a little bit. 2 to the power of 3. So 2 to the power of 3 is 2 times 2 times 2, which is 8. So what we're going to do is we're going to take 761 divided by 8 is going to give us the activity, so how many decays per second will it have after 3 half-lives. So let's grab our calculator here. So 761 over 8. looks like that's rounding off to about 95 becquerel. Or you could do 95.1 if you go with three significant figures there, 95.1 becquerel. Okay, so example number 3. I'm going to use a different color for example number 3 so it's easy to follow. The activity of a particular radioisotope falls from 160 to 5 becquerels in 12 hours. Calculate the half-life of this radioisotope. Okay, so it's gone from 160 decays per second to 5 in 12 hours. So let's figure out how many half-lives it's gone through. So what we're going to do is we're going to divide 160 by 2. That's going to give us 80, so that's 1 half-life. 80 divided by 2 is going to be 40, so that's 2 half-lives. 40 divided by 2 gives us 20, that's 3 half-lives. 20 divided by 2 gives us 10, which is 4 half-lives. And we're going down to 5, so 10 divided by 2 will give us 5. And so that's 5 half-lives that it's gone through. So the half-life, that took 12 hours. So it's gone through 5 half-lives in 12 hours. So if we divide that, that is, what is that, 2.2? Let's punch that in, just to double check, 2.4. So 2.4. So that's the half-life, 2.4 hours. Okay, so that's question number 3. And that's everything in black was question number 1. Okay, so question number 4 now. The half-life of a particular, I'm going to switch this up to do question number 4, just section that off. The half-life of a particular radionuclide is 7.5 hours. So half-life is T1/2, 7.5 hours. When measuring the activity, the Geiger counter is indicating 470 decays per minute. Okay, so let's leave it as minutes per minute. But you know there's background radiation at 30 decays per minute. Okay, so there's background radiations at 30 decay per 1 minute. And so predict the Geiger counter after 22.5 hours. Okay, half-life of 7.5 hours. So let's figure out how many half-lives it's going through first. So 7.5 hours is 1 half-life, plus another 7.5 hours is 2 half-lives. That's going to give us a total of 15. So it looks like 15. We're trying to reach 22.5, right? Yeah. So that plus another 7.5 is going to give us 3 half-lives, is going to be our 22.5. So it's going to go through 3 half-lives. And so what's going to happen is, if the initial reading was this with background radiation, so without background radiation would be 470 decays per minute minus 30, so 440. This is the actual reading, or so the actual decay without the background noise, without BG. So the background radiation. So that's the number that it is going to shrink by 3 half-lives. So we're going to do a 440. 3 half-lives is 2 to the power of 3, or 8. So 440 divided by 8 is going to give us 55. So that's what it's going to have. That's without background radiation, though. So so the actual reading with background radiation is going to be 55 plus another 30. So it's going to be 85 becquerels. Okay? So last one is example number 5. Lead of 221 has a half-life of 36.1 minutes, very precise. An initial example of 104 grams of lead. How much lead will have decayed after 144 minutes? So let's first figure out the time and the half-life first. So we have 144 minutes. This is question number, sorry, not 4. That's 5, isn't it? Yeah. Question number 5 now. So total time of 144 minutes and 36.1, right? Yeah, 36.1. And so let's calculate that out. So that's giving us about 3.98. So that's pretty close to 4. So approximately four cycles or 4 half-lives. Okay, so it's gone through about 4 half-lives. Whoops. And so 4 half-lives of 104 grams. So 104 is going to go through 4 half-lives. So that's going to be 16 then. 104 divided by 2 to the power 4, which is 16. So we're going to be left with about 6.5 grams left after 144 minutes. Okay, I think that is about it. Right, guys, hope that was clear enough for you to understand how some of these questions might work. Good luck with the cognitive questions, and as usual, let me know if you guys have any questions. See you next time.